Okay, cool. I think we'll get started now. Okay, so hi everyone, I'm Greg. I'm one of your GSIs, well, in case you don't know that. I'm giving a guest lecture today. And I guess the first thing is class notes. You have homework 5, it's due on Tuesday, and then you guys are free. And by free, I mean you guys are free to do your projects, which are due soon after. So yeah. Any questions on like class notes, class logistics, when things are due, anything like that? Okay, cool. So today, what I'm going to talk about is real-world robot learning. That's kind of, I guess, what my research focuses on. So I guess I'm biased, so I'm going to give a talk about that in general. And kind of the two aspects I'm going to focus on are safety and flexibility. So what do I mean by safety and flexibility? Well, I mean, for safety, you have these real robots. When they fail, for example, when you have your environment and you call env.step and done, like what does done actually mean? Well, that's what like done actually looks like in the real world, and it's pretty brutal. So that's one aspect that we're going to talk about. And the other aspect is flexibility. In all of your homeworks, or I'm pretty sure, yeah, all of them, you train kind of a policy for one task. Not necessarily in homework 5. If you're doing the meta learning, you're kind of getting a flavor of this. But having a policy that does more than just one thing is super useful in the real world. For example, here on the top and bottom, you can give it directions. You know, go left, go right, go straight. And it doesn't like naively follow it. It turns left, you know, when it's still on the road, when there's like not an obstacle. So these are kind of the two aspects we're going to focus on today. And okay, two topics, safety and flexibility, and for each of those, I'm going to go through 3 different papers, one focusing on imitation learning, one focusing on model-free methods, and one on model-based. So you can kind of see how each of these ideas can kind of get pushed into each of the topics that we've covered in this class. So you can think of kind of homework 1, homework 2/3, homework 4. These would be things that you could just add on top of them. And I guess as a caveat, I'm presenting kind of 6 papers and 6 overviews. These are not the best ideas necessarily. They're not as kind of representative of the literature or anything like that. They're kind of just things that I'm more familiar with, so they're biased in that way. Cool, and then at the bottom, I'm going to keep track of where we are, whether we're on safety or flexibility, and imitation learning, model-free or model-based. And feel free to ask questions during this. This is kind of more informal once we're kind of in the advanced topics of the course. So any questions, just throw your hand up. Cool. Okay, so the first topic that we're going to cover is safety and imitation learning. I guess there's some work that I did a little while ago called Play-Doh. I think Sergey might have talked about it a little bit in the imitation learning, kind of when you guys were talking about Dagger. But he did not talk about the safety aspect, so that's what I'm going to focus on today. So as a brief overview, I'll kind of skim quickly through this. Our goal is to learn a control policy that maps observations to goals. Our observation might be some onboard camera image, and we want to learn a policy pi theta that takes as input this observation and outputs a control U. Maybe this is the rotor speed of your flying quadrotor. And we're going to parameterize the policy as a neural network. So what we've always been doing, and kind of that's imitation learning in a nutshell. So we're going to kind of do a little bit of a deviation from standard imitation learning. So kind of the basis that we always assume, though, is that you're able to generate good trajectories using an expert policy pi star. Now, what is pi star? Typically, it's going to be a human expert. I mean, here's an example of someone who's sitting down, flying their quadrotor. If you have a robot arm, maybe you're physically moving the arm through space. If you're driving if it's an autonomous car, maybe you're just actually driving the car. So I'd say that's kind of the standard approach for imitation learning. The less standard approach, but one that's common, is to use like a computational expert. So for example, you could use trajectory optimization. Now, what do I mean by this? So let's say we have our quadrotor, and it's trying to fly around this obstacle right here. you could define a cost function that says, based on my current state and a sequence of actions that I take, how good or bad is the trajectory. And then you can define an optimization that says, okay, find a sequence of actions that minimizes this cost function. And what this assumes is that you're able to know the full state of your robot in the system. So in order to solve this optimization, you need to know where your robot is, you need to know where the environment obstacles are, you need to know everything. So in order to do this, you have to actually get this full state information. And you might do this by maybe instrumenting your environment, by having like sensors that detect where your robot is, and then you can actually solve this optimization and plan for a sequence of actions. And voila, it'll fly around, and you'll have your expert pi star. It's doing what you want. Now, this might seem a bit limiting. You have to actually instrument your environment. You need to know where everything is. But the key thing is that you only need to do this during training. So during training, you'll instrument the environment, your quadrotor will fly. Then you just train the policy to take as input the observations, which you always have. You always have the onboard camera, things like that, to match the controls. So we're kind of doing this, I guess I call it a bait and switch. At training time, we assume one thing, but we only train with one part. And then at test time, you can actually deploy it without instrumenting the environment.
Why do you need to instrument that environment?
Because you need to evaluate this cost function. So this cost function encodes the task that you want to do. So the task, let's say in this example, is to fly and not crash. In order to fly and not crash, I need to know where my robot is and where the obstacles are.
I see, but you don't have a camera on the robot?
So we have a camera on the robot, but I'm going to say that the RGB image on the robot doesn't tell you what, it doesn't directly tell you about the environment. So a camera image doesn't tell you the XYZ location of obstacles. You could, I mean, there's a lot of methods that go and do that, and you could do that. I'm just saying that you have to put in effort to actually make this work. This is kind of this more standard robotics approach for like path planning and things like that.
How do you define the post function? Either success fail or there is?
So this is, defining C is, I mean, it's going to depend on your problem. I guess to relate this back to homework 4 in your model-based learning. So homework 4 was trajectory optimization, what I just presented here, but where you learn the model of the world. So in that homework, let's assume that the model was known and perfect. We defined the cost function for you. So I think you were doing half cheetah, and we defined the cost function as run forward as fast as you can. If you want to do something else, you have to redefine the cost function. So this is, yeah, manually designed.
Does it have to be convex? Or should it be convex?
So yeah, the more complicated C is, the harder it is to actually solve this optimization. So I guess there's two things. One is the cost function convex. Now let's say it is. That could make things nicer, but if your dynamics are non-convex, then it's still going to be a mess anyways. So yeah, so for solving things like this, you'll need some pretty powerful tools. Yeah, non-convex optimization. Cool, yeah, any more questions? Okay, so going forward, I'm going to assume that we're actually using trajectory optimization for the expert. And this is going to matter because we're going to be kind of playing with the cost function and kind of interpolating between the two. It's kind of hard to interpolate between you and what the human is doing. This will become a bit more clear in a few slides.
T, the capital T is the end of episode?
Yes. It's either the end of the episode, or you're predicting over a short horizon and doing model predictive control like you did in homework 4. Yeah, either one of those. Okay, so now if we wanted to do imitation learning, I'll go quickly through these slides, but pause me if you need to, is to just do supervised learning. So we gather expert trajectories using our trajectory optimizer, and then we do supervised learning to map the onboard observations to controls, map O to U. This is what you guys did in homework 1 as the very first step. And this works okay, but there's a problem, which you guys should know about, is that if our training trajectory is like this, and we actually run our learned policy, it's very likely to actually diverge. So why does it diverge? Well, if you make a little mistake at the beginning, you get these compounding errors until you eventually just completely explode. And the main thing is that the policy, even though there's little errors in the beginning, a tiny error gets you to parts of the state space that you've never been before. And when your policy gets to somewhere it hasn't been before, it's likely to do something even worse, and boom. So this is kind of what Stefan Ross in his paper Dagger, what they kind of noticed and what they kind of addressed with Dagger. So our main problem is that the training and test distributions differ. Now this is where Dagger came in, and this is, I guess, was homework 1 part 2. So you have your training, your test distributions, they differ, and we want to solve that problem. So our solution is to actually execute the policy during training. So what does this look like? Well, our policy is some mixture of pi star and of pi theta, where beta is just some, it's like a coin flip, some value between 0 and 1. So yeah, every time step you flip a coin and you decide which one are you going to execute. Now what does the learning loop look like? Okay, first you gather expert trajectories. Maybe you have like a car driving around some track. And you aggregate your new data with your old data. I mean, this is data set aggregation. This is the aggregation part. And then you do supervised learning to train your model to match the expert. And you repeat this loop. And when you repeat this loop and gather expert trajectories, you're going to gather it according to pi mix. Any questions on Dagger? Okay, so now let's talk a bit about safety in Dagger. So Dagger mixes the actions. So like I said before, it's kind of a coin flip between whether you execute pi star or pi theta. And this can actually cause some issues with regards to safety. So let's say we have this obstacle that we want to fly around, and we start at the red x, and our coin flip parameter beta is 1/2. You might get something like this. On the first step, you execute an action, and you choose to execute pi star. Then maybe you're like, okay, the next coin flip, I execute pi theta, then pi star, then pi theta, and then boom, you crash. And this can actually happen, like we ran this is running Dagger, this is our quad rotor flying, and it has some coin flip, I forgot the exact value, and it's doing well for some time, but then eventually it crashes. Now this is, I guess, problematic. Let's not ruin it too soon, because we wanted to use Dagger in the first place so that the training and test distributions differ, but by executing pi theta, we don't know how good pi theta is. It might be bad and it might crash. So now we have these kind of safety versus policy performance, and they're kind of pulling us in two different directions. So we'd like to come up with a method that can kind of smoothly interpolate between the two, so that when it's near a dangerous situation, it just does pi star, and then when it's near a safe situation, it mostly does pi theta. That's kind of the behavior that we want. Are there any questions about Dagger's issues, motivation? Okay, so this is where Plato comes in. So the idea with Dagger was to mix the actions. Now with Plato, what we're going to do instead is we're going to mix the objectives. So by mix the objectives, here we have j pi, and j pi will be the cost of the expert. So this is, if we just got rid of, if we crossed out the second term, this would produce pi star if you optimize j. So that's kind of the pi star part of the objective, and the pi theta part of the objective is to say, okay, I want to be as similar to pi star, but also be similar to pi theta. And this is some lambda weighting between the two. So now we're going to kind of have these two terms are battling between pi star and pi theta. And in order to get the policy, we solve this optimization, and we can get kind of u lambda. So how is this actually going to look like when we actually execute it? So let's consider the same scenario. So you're always going to be executing pi lambda. But what's going to happen is in the beginning, let's say we're very far from any obstacles, any dangers, or any high costs. So we can be more like pi theta. Now, as we get closer to the obstacle, the cost is going to go up. So if pi theta wanted to go towards the obstacle, that'd be penalized very highly. So now we're going to be more like pi star, and then it'll actually fly around. So kind of the cost j is preventing us from doing anything horrible, but the KL divergence with pi theta is making us be as on policy as we can. Any questions about how this kind of solves the problem?
Do you still add your data into your buffer, like dagger?
Yeah, so this is going to be the exact same loop that we saw in the previous slide, the same dagger loop. We're just changing the policy. Yeah.
I think KL divergence is only suitable for the stochastic policy.
It's only for stochastic policy.
KL divergence is only
Yes.
for stochastic.
So
Policy must be stochastic.
yes, I mean, we can just say some Gaussian policy with some noise. I mean, in practice, this turns out, even if you're just doing deterministic, you can just have this be kind of like the L2 norm between them as kind of, I guess, a heuristic. But yes, you're right. So one thing I'll point out is in the very beginning, I said that we needed to do trajectory optimization. And this is the reason why. We had to solve this optimization that interpolates between what the expert wanted to do and what we wanted to do, the on-policy part. So you couldn't solve this if you had a human, because the human is doing J inside their head, and you can't ask them to interpolate between them for you. So that's why we have trajectory optimization to do that. Yeah?
What would happen if, like, pi lambda started to find like a better path than the human would have? We would start to get punished, right? In some sense.
Yes, so I guess this could be, if you did it with a human, you'd have another complication where they might have hidden preferences that could be a bit hard, like maybe its goal is to avoid crashing, but just always prefers going left. But maybe pi lambda found a good way to go right, and now they're clashing. But because you have this j of pi, I mean, that is encoding what you want to do. So I don't think you'll run into that issue. That's a good question.
How do you actually implement this KL divergence? If it is a Gaussian, it's easy to write the KL divergence.
Yeah.
Here, I think it's not that easy.
So it's the KL divergence of the output. So this is kind of what you guys have been doing in all of your homeworks. For example, if you're calculating the probability, you do log prob all the time. So you're doing log prob between your policy, which we usually make it a conditional Gaussian. So yeah, this is like if you did Gaussians, it would just turn out to be like an L2 norm. So yeah, it's typically not a problem. If you wanted to have a more expressive output policy distribution, then yeah, it might be hard. But for this, in general, it's okay.
But pi is the output of the neural network,
right? Right, so we say that the neural network outputs a mean and a standard deviation. Yeah.
It's the K divergence between which policies?
It's the KL divergence between our current learned policy pi theta and this policy pi that we're optimizing for.
Which is not pi lambda?
It will output pi lambda, so it's argmin of pi. So find the policy pi that has low cost j and is similar to pi theta, and output that as pi lambda.
So it's completely not related to pi star.
No, it is, because pi star was generated from j. So this term, if you only had the j, and it was just argmin of j, that would get you pi star. So yeah, the pi star term, pi theta term, and interpolate between the two according to lambda. Okay, so some kind of a quick overview is, first we had supervised learning. The sampling policy was pi star. This is safe by definition, assuming you have a good pi star. Pi star should be safe. But the issue is that the training and test distributions are not similar. So then we went to Dagger. Dagger has the sampling policy pi mix, the coin flip again. And it was not safe because you might be executing pi theta, your learned policy, and that might be bad. but it does have similar training and test distributions. So that was the motivation for Dagger. And the idea for Plato is that it kind of gets the best of both worlds in some sense by being safe, because it has this it dynamically chooses when to be more like pi star, when to be more like pi theta. But it also has similar training and test distributions because of this KL divergence term. And now just for some brief experiments, here's a video of the final neural network policies, both for quadrators that are flying based off of kind of little camera images. And as you can see, I mean, they can learn a good final policy. Now this is kind of not too surprising. You guys did homework 1, you did Dagger, and it worked fairly well. Like for example, humanoid was super hard, you do Dagger, and you're able to get up to that 10,000 reward. But the thing that we care about is actually the training process. How did we actually get the data in order to train this policy? So here on these are the two environments, the canyon and the forest that you just saw, and this shows the performance. In black is Plato, and all the other lines are other methods, and higher is better. So as it goes on, it's able to learn better and better. Now, the other thing that we care about is how often does it crash? How often does it fail? So here's the training iteration and the number of crashes. And as you can see, let's see, I think Dagger and the variance are kind of the dashed green lines. They crash during learning, and that's not okay. While kind of Plato in black crashes much, much less. Now you might ask, okay, why does Plato never crash? The whole point of this was to get them to 0. There's two things. One, if pi star, in our case, wasn't perfect, we were solving, like he said, a non-convex optimization, so sometimes that can mess up. And there's also that weighting factor lambda that trades off between the two. If you set it wrongly, you might not actually be safe. Now, as another motivation, you might say, okay, the issue with Dagger is that beta coin flip. So let's not come up with a new method. That's too much work. Let's just set that coin flip parameter correctly. But you can run into an issue. So here's kind of a semi-contrived, but maybe actually semi-realistic scenario, where first you start off in a forest, and then you switch to a canyon environment that you've never seen before, and then maybe you switch back to the forest, and then you go to the canyon. It's kind of hard to set this beta parameter when you don't know the environments your robot will be in. So you could try to set them intelligently first, but now you go to the canyon, and your number of crashes for Dagger will just shoot up because you've never seen it before. Now the idea, at least with doing something like Plato, is that it knows when it's going to mess up. So it's less heuristic-y, and it's more likely to actually be successful and safe. Okay, any last questions before we move on from imitation learning to model free?
Why Plato can transfer between different environments?
Because this, let's see, this optimization here is being run at every time step. So it's trading off between j of pi star and being similar to pi theta. So if you went to a new environment, pi theta might be horrible. And because it's never seen it before, it's just going to do really, really bad. So in that case, it'll automatically know that I should focus on just minimizing j and being more similar to pi star.
If you know the model dynamics, can you replace the fully observed assumption with a state estimator? Or it would still be observable, but observed assumption?
Yes. I guess, yeah, as long as you can solve the trajectory optimization by whatever assumptions you need to make. If just doing your own state estimation, that would be fine. And I'd say, the main limitation, I should say, of this method is the state information assumption. You can try to get rid of it by doing your own state estimation, your own kind of path planning. Those are highly non-trivial.
So your trajectory optimization, is it the same as MPC? You take the first action?
In our case, yes. In general, you can use whatever optimizer you want. Okay, let's move on to model free. So this is a paper called Safe Reinforcement Learning via Shielding. Again, in general, it's the same exact goal. Here's our standard reinforcement learning loop. You have your environment, you get some reward, your learning agent takes an action, and you do this loop. And kind of by construction, there's nothing at all in this formulation about safety. So what they propose is this method called shielding. And kind of the motivation is to prevent the agent from doing anything stupid. And they kind of present two types of shielding. The first they call preemptive shielding. So again, we have this environment learning loop. And what they do is when the environment gets an observation, the shield computes the set of actions that are safe. And then the learning agent can only learn from this, can only execute this safe action set. So basically what this is doing is it's learning in a transformed NDP where you can't do anything wrong. This or maybe an analogy would be, let's say you have a child is walking around and the parent is always walking behind it. And if the child is about to walk into traffic, the parent will hold it back and prevent its action from actually going forward. So that's what preemptive shielding is. They also have post-posed shielding. So this is similar, but you're kind of putting the shielding on the other side. So we have our environment, you get the reward, and the learning agent from the current observation decides what action it should take. Now once it decides what action, the shield says, okay, let's filter that out. If you decided to do something bad, let's change it to a good action and just execute the safe version of that action. So the nice thing about doing this is that you can use the shield at test time, and it'll just interface with whatever policy learning method you did. So you could run your standard reinforcement learning method, and then just at test time, put this shield on, and you'll be good to go. So now let's think a little bit about what are the pros and cons of each of these approaches. So let's actually start with post-posed shielding. Can anyone think of a reason why this might be a bit weird? Think about it kind of during policy learning. You're doing Q learning and you say, I want to go left. And now the shield says, nope, you're going right. And this gets added to your replay buffer.
The policy doesn't reflect what ended up happening.
Yeah, exactly. Yeah, I'll repeat it for people watching. Yeah, the policy doesn't reflect what actually happened. Now you can kind of play around with this, but it can be kind of a bit weird. You can imagine an extreme scenario. Let's say I'm allowed to take 100 actions, and they're all terrible. So the shield just says, nope, you're going to do the one safe action. Now I have to learn that in that state, doing any of those 100 actions will all lead to the same outcome of doing this one action. So it kind of adds this extra layer of complexity that your policy needs to learn about.
But doesn't that you just write the safe action within the replay buffer, and then your policy will learn that, and then you will not need the shield?
So that would actually get into preemptive shielding. I guess another way of, so that'd be more like preemptive shielding. So now an issue with preemptive shielding is kind of this, I guess, solves the issue that we just talked about, but then at test time you can't, well, okay, but the nice thing is at test time you don't actually need the shield. Now, is there any reason to do, it kind of seems that preemptive is kind of the better one to do in general. I guess, the main downside is the agent could still, at test time, output an unsafe action because you don't have the shield. There's nothing between the learning agent and the environment to make sure that you only do something safe. So there's actually no guarantees on this method being safe at test time. That's the downside of preemptive shielding. Yeah, so you can for sure do both. So there's no issue with that. You just need to make sure that you can actually evaluate and do your shield at test time, and that'd be fine.
Why can't you add the shares at the testing time?
You can. It's an additional assumption. I haven't even talked about how the shield is actually computed, so that'll I'll go into that in the next slide, and that'll show you kind of what assumptions do you need to make to even evaluate what is safe and what is not.
And what is put into the replay buffer, the safe action or the action?
You can, I believe you can try both. One of them would be, if you put in the safe action, it's more of a dagger vibe, because in dagger you execute some action, but then you label it with pi star. So if you did that, it'd be more like that. Which one's better? I'm not sure. So now getting into what the shield actually is, how they do it in this work is they encode it with temporal logic. Now, in order to encode it with temporal logic, they need to make, I would say, very, very strong assumptions. And the very strong assumption they need is that they need to know approximate or possibly conservative transition dynamics. So one of the examples they give in the paper is you have this task of keeping a water boiler full. So you want it to not run empty, which is at the bottom, but you don't want it to overflow at the top. So what they assume is that they have some temporal logic that they can say that encodes a conservative estimate of how fast you can fill it and how fast you can drain it. So because it's conservative, they can then have this be the shield and make sure that the actions don't fill it too fast or don't drain it too fast. So this is, I mean, this works fine in this example right here with this water boiler, because we kind of can characterize the system as engineers. But if you go into a general environment, like let's say you want your half cheetah to run, and you don't want it to ever fall down, because that would break your half cheetah. You would need to be able to have some conservative dynamics that makes sure that, you know, the center of mass is always above 10 centimeters or something like that. And you would need to go and code this up. And that's, like, I personally don't know how to do that. Maybe if someone is very, very good at modeling, they could give this to you, but in general, it's pretty hard. Another example in which this would be hard is autonomous driving. The car is driving around. You would need to know the approximate dynamics of your car and of the environment. That includes other cars, bicyclists, pedestrians, and that is also in of itself hard. So these are fairly strong assumptions. Yeah.
How do you build the shield, like in this case of the car? I think it's kind of difficult.
Yeah, so I'd say this method gives you pretty strong guarantees. Like, it actually does give you safety at the cost of very, very strong assumptions. And this is kind of, I think, one of the main themes of safety is that if you want guaranteed safety, the only way, perhaps someone can argue this with me, the only way I say you can guarantee it is if you know the dynamics of the world, you and the world. That's hard. So kind of these methods make trade-offs between assumptions and guarantees. And that's kind of the game that's played.
So with that statement, can you really have model-free safety?
Without making strong assumptions, I would guess I would say no. Yeah. Okay, so now on to some experiments. So in this experiment, they wanted this car to learn to drive in a circle, and the safety constraint was don't crash. So I didn't put the equations up here, but they put some equations that had some conservative estimates of how fast it could go in steering. And here it shows the learning curve. And as you can see, no shielding is the red line, and with shielding is with the blue line. And I think that was post shielding. Preemptive shielding is in green. And that shows it's able to learn with this shield, but without ever crashing if you do the post shielding.
The reward is only how fast or how safe. Is there any safety in the reward?
The reward, I think, is just to actually go around in a circle, and I think if it crashed, you got some negative reward. So that's one example. Another one that's actually, I think this was a good test case, was on the game of, I think this is called Sequest, right? So the goal is that you are
this diver right here, and you are trying to go down and pick up these things. I forget what they are. Oh no, you're the submarine. You're going to try to pick up the divers, and people are trying to shoot you and destroy you, and you also have finite oxygen. So what they did is they encoded some temporal logic that was conservative. Like they kind of knew how quickly oxygen got depleted, and they said, okay, make sure you never run out. And this would make the agent always be forced to surface before it ran out of oxygen. This is the learning curve. There's no difference between the blue and the red lines with or without shielding. But the key point is that you get the same learning performance, but the agent never died from running out of oxygen. So this is good, and this is kind of what we want. Let's see. Okay, any questions on this model free for safety? So shielding in this case was linear temporal logic. So you said, if you are below this level of oxygen at blank time steps into the future, which they coded up with some conservative dynamics, then it's not satisfied. So they had some logic that said you must always satisfy this. And that's how the shield chose which actions were valid and which were not valid. Okay, so now let's move on to model-based. This is some work that we did a little while ago, and I guess the main difference from the previous is that this is going to, this does not guarantee safety in any aspect. It's kind of trying to minimize the amount of damage that's caused, but it's more, it can be applied to more practical scenarios. So kind of the assumptions versus capability. So what's the goal in this work? The goal was to do reinforcement learning without destroying the robot during training using only onboard images. And so we want a quadrotor thrown here. There's some obstacles that it has no idea about. How do you learn to navigate through them without destroying the robot? Now in general, this is basically an impossible problem. If you don't know something about the world, how can you ever avoid it if you never experience it? So kind of the main idea we're going to try to do is minimize how bad things, like how bad the things we encounter are going to be. So what we do is we encode our task as a cost function, cost of tau, which is a trajectory, into the cost of the task, which might be fly at 2 meters per second, plus some cost of collision, or basically cost of like failure, like doom. Now what we're going to do is we're going to learn a model, a collision prediction model, that takes as input the current state observation, which might be a raw image, a sequence of actions, which could be commanded velocities, and it outputs the probability that you will collide. And we parameterize this as a neural network. So what we're, at a high level, we're learning a model that predicts when the end of the world is going to happen for our robot. So at a high level, what is this collision prediction model? It's a neural network. I've replaced all the layers with a bunch of clouds. So again, it takes as input the current state, image, and a sequence of actions, such as, well, I took this from our car, such as steering angles, and outputs some value between 0 and 1. Am I going to collide or not?
So it's a recurrent?
Yes, so this is a recurrent neural network. So this should give you a vague reminder of homework 4, your model-based. So in homework 4, what you did is you took your image and an action, and you predicted, let's say your image is your state, so you took your current state, current action, predicted the next state, and repeatedly applied it. But here, we don't really want to predict future states. We don't care about future images. We just care about collisions, what happens in the future. So we don't reconstruct the next state. We just keep everything in the latent space in the neural network and directly predict collisions.
So that is the one-dimensional scalar?
Correct. So yeah, this output here is just one-dimensional.
The probability.
Yeah, it's a one-dimensional probability, but for multiple time steps into the future. So our model, for example, is planning 3 seconds into the future. And every maybe quarter second, it outputs, did I collide, did I collide, did I collide?
So that's our collision prediction model, but how are we actually going to get safety? So here's a high-level view of the model-based RL approach that we took. So first, we have some data that we're going to be continuously adding to, and we train an uncertainty-aware collision prediction model. So I talked about the collision prediction model. I haven't talked about uncertainty yet, which I'll get into in the next slides. And what this is going to be is a deep neural network with uncertainty estimates from bootstrapping, which I think Sergey talked about before, and also dropout. So these are kind of modern methods. Well, some of them are old methods renewed for neural networks, but methods to get uncertainty estimates from our neural network model. Now with this model, we're going to form a speed-dependent, uncertainty-aware collision cost. And what this is going to do is it's going to encourage safe, low-speed collisions by reasoning about the model's uncertainty. So we can't guarantee that we won't collide. We don't know the environment. That's just an impossible task. But at least when we get more uncertain, can we fly slower? And if I crash at low speed, that's not as bad. That's an assumption we're making. Now the next step we're going to do is with this cost function in this model, we're going to gather trajectories using MPC controller. This is exactly what you guys did at homework 4. And you might experience collisions, like I said, but the idea is that you would hopefully experience these collisions at lower speed. You would learn what in the environment caused this, and you become more and more confident. You'd be able to fly at higher and higher speed and kind of get better as this loop continues. I'm going to go into a bit more details on kind of the different aspects now. So first is the collision cost. So this is our collision cost. First, we say if you're going at high speed, you should have high cost. If you predict collision, you should have high cost. And if you have large uncertainty, like high variance or high standard deviation, you should have large cost. This is just some cost function we made up. Mean plus variance is just one way to do it. There's a lot of work in risk-averse reinforcement learning. Also, people who do learning for trading on the stock market and things where doing bad is worse than doing good. They tend to look into these different kind of cost functions. So there's a bunch out there. You can do something else as well. Now the next is estimating neural network output uncertainty. So we use two methods. First is bootstrapping. I'll go through quickly since Sergey already covered it. At training time, you take your data set. You resample with replacement multiple data sets. For example, if this is bootstrapping with 3 models, and you train a model for each one. Now the idea is because they're trained on different subsets of the data, they'll agree in some areas, but disagree in areas where the data is different, where you have like not that many data points. Now at test time, you take an input, you pipe it through all of your models, and you combine them to get a mean and standard deviation. So the nice thing about this method is this actually isn't specific for neural networks. This is any model you can train with data. So it's very, very general. One of the main downsides is it's very expensive. You have to train a bunch of models, and at test time you need a bunch of models. So depending on your application, this could be a bit painful. The next method is dropout, which I would say is a cheaper version of bootstrapping, but might not perform as well. So for training time, for those of you who aren't familiar with dropout, you take your data and you train your model, and at each time you call gradient descent, you randomly drop different weights from the model. Now dropout was originally designed to give you robustness, basically to prevent overfitting, but there's a paper that showed that this can actually be related to uncertainty. So now what you can do at test time with this model is you take your input, you again do the same exact thing, you drop different weights, and these will actually give you slightly different outputs. This is very similar to bootstrapping. And now with these slightly different outputs, you can form like a mean and standard deviation, or some distribution using that. So yeah, one nice thing is this only requires one model and just multiple forward passes, so this is fairly efficient to train and at test time. One of the downsides is the models are correlated. So dropping some weights, these models all have a lot of overlap in kind of the distributions they'll output. So in this sense, it's kind of an approximation to bootstrapping. It might not give you as good of uncertainty estimates. Any questions about uncertainty?
The dropout is a neural network, right?
Dropout is, yeah, so this is a neural network, and dropout randomly drops connections in your network.
I think it was half of the net, half of the,
Um,
in the original.
It depends. Maybe in the original, but you have this p parameter that you get to choose how many drop out.
But I have another question about how you define the ghost function. So there you look at the square root of the variance, and apparently it will be very high when you reach states that you didn't say in the past, and thus you will always have a large cost and make bad decisions because you weren't there.
Right. So, yeah, so, okay, now we get into, I guess, a topic. Let me come back to that. You're getting into, I guess, exploration versus safety. I'll talk about that in a little bit. That's a good idea. Okay, so that's the kind of the end of the method. Now some preliminary real-world experiments we ran a while ago. This is what happens if you don't account for uncertainty. It just kind of goes full speed ahead when it hasn't seen it and crashes and out. Now, if you account for uncertainty, we can't say that it's never going to fail. But at least when it didn't know, it kind of bumped into it slowly and it survived. Nothing too horrible happened. And kind of the hope of the method is that even though it crashed at low speed, it learned something about the environment. And it's able to generalize that a little bit and make more and more progress. And eventually, it is actually able to fly around the obstacle. And during training, it experienced less collisions, less failures because of the method. Okay, so that's the end of the safety part. And kind of some takeaways, getting back to what you were talking about. There's a big trade-off between safety and exploration. I didn't really talk about this trade-off at all in any of these works. Kind of one of the main things that people tend to do in safe RL research is they focus on problems in which safety and the task are in line. If I have an autonomous car, part of its objective is to be safe. But what if you have some task in which you need to do something risky in order to actually learn what to do? I think that's a much, much harder problem, and we're pretty far away from that. Was that addressing what you were asking?
It's kind of like this airplane that you showed on drone.
Yeah.
At a certain point, it will reach something an area that's not familiar with. So how the safety can help you there?
Yeah. So I guess the hope is that maybe if you go to a part of the state space that you've never seen, that you can still take actions that might minimize damage, but you're still in the state space. So like I saw the obstacle, so even though I didn't see it and fly at high speed, at least I saw it and flow at low speed, so that I can still learn about the environment. So there's an interaction between the state space and the action space. But that's a finger crossed, hoping that it generalizes. Let's see. Yeah, another takeaway, which I talked about a bit earlier, is that safety guarantees require either an expert to always be there, ready to take over, or known environment plus known dynamics. Besides that, I doubt that you can actually get any guarantees. And the last thing is that I think uncertainty can play a key role. That if your agent doesn't know what to do, that can still inform it about what's better and what's worse. It can at least try to do things that aren't horrible. Okay, any questions about safety before we transition to flexibility? See how much time we have.
The input is an image, if that's time-consuming for you to go out that policy.
For the prediction model?
Yeah.
I mean, I guess it's not too expensive because we're not predicting future images. We're just predicting single scalars of collision. So keeping everything in the lane space of the RNN, it's not horrible.
Do you use the CNN first to extract some future?
Correct, yes. Yes. Okay, let's take like a 2-minute break and then we'll start on the next part.
to reply to a question I posted on Piazza about DQN learning, and then if you continue the learning,
It just goes down, yeah.
Yeah. Is it normal? Like, is this behavior normal, or?
Yeah. So I mean, DQN can be kind of unstable. That's why they all have the whole replay buffer and target flipping and things like that.
Mm-hmm.
So I'm not too surprised that performance can go down. I mean, you could maybe find a hyperparameter setting that would fix it, but it seems like you tried very, very hard.
Yeah.
So
Yeah.
I don't know what else I would try.
Just stop it at the peak.
Yeah, I mean, not necessarily even stopping it. You could, I mean, you can keep all the checkpoints and just take the best. Another thing is you could, at every checkpoint, you could say, okay, if my current policy is worse, like during learning, update to be the best policy I had to make sure you don't get any worse.
Yeah.
That can mess up exploration.
Yeah, but it's weird. Like when you reach the top, it should fill the play buffer with good rewarding stuff, and then learn.
Right, but like I mean, something you could try is take an expert policy, have it fill a replay buffer, and train a queue network. It probably won't work.
Oh.
Because it's important to learn what not to do
Mm-hmm.
and what to do.
Mm-hmm.
That's how you get a good policy.
Okay, so you still need some randomness.
Probably, yeah.
Okay, great. Thank you.
You had mentioned, I'm familiar with dropout, you mentioned it could also be used for uncertainty.
Yeah.
Is this the paper maybe that you
Yes.
refer to?
There's also a blog post on it.
Okay.
I think that was much more intuitive. They have like little things you can play
Same
around
authors?
with. Same authors.
Okay.
Just go to his website, Young.
Perfect, thanks.
Yeah. Okay, let's start up again. And now we're going into the flexibility part of the talk. So now we're back to flexibility, but we're going to start with imitation learning again. So we're going to start with this paper called End-to-End Driving via Conditional Imitation Learning. And I think this paper is, the method is actually very simple, but I think they get very good results, so that's why I like this paper a lot. So the goal is pretty simple. Normally, when you do imitation learning, you do something like this. You try to learn a policy that takes as input state and output actions, and you want it to be as similar as possible to an expert pi star. Now, kind of the problem statement is that they want to now also take as input a user-specified command. This command might be to go straight, go left, go right, and have it still imitate the expert while kind of going where the human wants it to. So here at the bottom, I showed an example where, so it starts to go straight, and that's all good. And now here it says to go left. Now, the agent doesn't just immediately go left. It knows that it should turn left only when the expert would have turned left, which is when this part of the road comes. And it successfully executes that. So that's kind of the behavior we want in order to get this flexibility, but actually doing the right thing.
So C it interacts with the user to mean that.
Yes, so I'll talk about how you actually get the C in there. So the approach, the first thing they try, I would say, is the default standard approach that I think most people would do, is where you just concatenate the command C with all your other inputs. So here they have inputs like an image. They also have measurements like how fast are the wheels spinning. And now they also concatenate that, and they learn a policy that eventually goes to output actions. So that's one architecture, kind of the vanilla one you would start out with. Now, the other one that they considered, which ended up working better, was that you take your network, which has an input image I and measurements, you pass it through a few layers, and you use the command C to decide which branch it should be on. So for example, the left branch would be these layers going up. This going straight branch would be this set of layers, or the going right would be this set. So you can kind of think of this analogously to DQN, where you take as input the current state and you output a head for the value of each different action. This is kind of multiple heads, but they're all outputting optimal actions that pi star would do.
I think this it can only handle the command C is not that big. If it's very big.
Correct. So I'd say, yeah, the main downside of this is it assumes kind of discrete controls. In this example, they were just doing driving, so left, straight, right. So I'd say that's the main downside. Empirically, they found it worked better. But I think this is definitely something to think about, especially for those of you very interested in things like Q learning. I mean, by default, a Q function takes as input a state and an action and outputs a value. But now, like DQN takes as input a state and outputs multiple values. Like they did that just because neural networks are hard to train and that got a bit funky. But like nowadays, we've learned enough so that you can actually train a Q function that takes as input the state and action and outputs a single value. So I'd say these are neural network tricks which can generalize sometimes. It can help, but they're not fundamental necessarily.
Can you repeat that again, please?
That kind of, we're playing tricks with how to organize the network in order to get better performance.
I mean the Q function.
The Q function.
Q.
So that was a bit of an aside. Maybe we can talk about it after. I guess if you understood it, great. If not, don't worry. But yeah, so architecture structure is unfortunately one of those things that as researchers you'll spend a lot of your time doing, but is not necessarily like fundamental, not necessarily fundamental or will generalize, although sometimes it will. Some of the best advances, like dropout, for example, was just an intuitive hack of sorts that they thought of and it worked great, and now they've realized this actually is something fundamental. Sorry, a bit of an aside. So that's actually the approach that they ended up using for training their conditional policy. Now, there's a bunch of other important details that they did, which is kind of the dirty details of getting imitation to work on complex environments and in the real world. One of them that they did, which I found very interesting, was significant amounts of data augmentation. I guess this is maybe unsurprising for people who are working in standard machine learning for computer vision, but it's always unclear if these will actually transfer to better policies. So changing contrast, brightness, tone, Gaussian blur, salt and pepper noise, region dropout. They would cut out like 1% of the image and just totally black it out. And this helped a lot with robustness. The other thing that they did is they added noise to the expert. This is kind of in the dagger style. So they added a bunch of noise, and then at some point the expert would take over. So this learned corrective behaviors and kind of would address the policy divergence issue that supervised learning, imitation learning tends to have. Okay, so that's kind of actually the end of the approach. Here's some videos. So they first trained in the Carla simulator. This is a realistic simulator also from these authors. Yeah, and it's learning from just the onboard images, as you can see. And it's, yeah, I'd say this is a very good policy. I mean, so, okay, it blew past that stop sign, but it's not hitting cars and it's not hitting pedestrians. I guess I'd call that a success. They also ran this on a real-world RC car. So they drove this RC car around this environment and recorded the actions that it took, and also the steering or the commands left, straight, and right that they wanted. And as you can see, it works pretty well.
Very fast.
4x.
Oh, 4x.
Yeah. They also tested the generalization, which I think is kind of one of the main things you need to actually test with imitation learning, because it's very easy to overfit. I think that one's pretty nice. It's just nice to see it's not blindly following the command. It's doing it intelligently. Yeah, any questions about end-to-end conditional imitation learning? So I'd say, yeah, just one takeaway is simple things are more likely to work on complex tasks sometimes. Fancy sometimes doesn't work great. Okay, now we're going to move on to a model-free method for being flexible. This is work done by Thomas and some other co-authors, also in Sergey's lab. If you're doing homework 5, the soft data critic, I think that's 5B. This builds on top of that. I'm not getting into that. I'm just presenting a very high level. So the goal, again, is to be flexible. So let's be able to accomplish multiple tasks at test time. So let's say our robot starts at this star, and maybe task 1 is to reach this yellow circle. And these are the rollouts it gets that are successful. All of them accomplish it, yay. Now, let's say we have a task 2, and the task 2 is to avoid. Now, there are a bunch of trajectories, and all of these avoid the blue triangle. So again, yay, we have good policy. But now what we want is something where we can combine these two objectives. So if we take the rollouts from both of these, we would see that these two ones that are darker both accomplish task 1 and accomplish task 2 at the same time. So I guess this would accomplish maybe the green task, which is the sum of the two. So given the space of trajectories, this is, I guess, the space of all possible good avoidance skills. This is the space of all good reaching skills. And the intersection is what will accomplish both of them. So the goal of this work is how can we take policies learned for individual tasks and combine them to get a policy that will accomplish the joint of the tasks. Okay, so policy composition. So to formalize this, we have task 1 and we have task 2. And you define some reward function that actually accomplished this. And then you learned a Q function in order to then extract a policy that it can accomplish each of these individually. And now we want to combine the two. So we basically want to solve the task in which we added reward 1 and reward 2 to get the composition of the two rewards, which is the task that we care about. So in essence, what we want is the sum of their Q values. But in general, this doesn't just work out of the box. So it'd be nice if you could just take DQN from homework 3, train it on task 1, train it on task 2, add them and get both of them to work together. This is actually not the case. It's a bit involved. So I'm not going to go into the details. You can look at the paper. But basically what they show is that how good the policy is, the composed policy, depends on how similar the policies for task 1 and for task 2 are. And that kind of says how good they'll be. So if there's basically how good the composed policy will be depends on the overlap in this region. If there's no overlap, it's not going to perform well. If there is noticeable overlap, then they'll do well. Now, how do you actually get this reusability? By having maximum entropy policies. So I think this has been talked about in a previous lecture, but by having maximum entropy policies and not just deterministic, you'll actually get overlap in the distributions. And that's how you can actually get this result. Yeah?
I'm not sure, how do you do this separation RC equals that and then QC? Because like you generate rollouts or do something, and what if?
For which one?
How do you run this algorithm? So let's say you have a policy that said do action A and the policy that said that do action B. How do you sum that?
You're not combining the policies, you're combining the Q function and then doing policy extraction on the Q function. So like we would take Q1 and Q2, combine them, which we can because they're maximum entropy Q functions, and then we do policy extraction on the combined.
You're doing a discrete action?
You could do discrete or continuous. So if you did discrete, it'd be fine because you could do your standard DQN max of all the heads. If you did continuous, you could do it by solving maximization. Or what they actually end up doing is they do an actor-critic style. And because you do actor-critic, your actor can output continuous actions, and that's how you do that. So basically, the main takeaway is you can add Q functions as long as you do this maximum entropy Q function. So it's what you would intuitively do plus just a little bit. But by a little bit, there's a lot of justification behind it. I'm just throwing that under the rug. So the main advantage of this that's super nice is you get reusability. You can train, let's say you have n tasks. You can train a policy for each of the n tasks, and then if you want to do task 1 and task 4, you combine them. You want to do task 1, task 3, task 4, you combine them. And things will work depending on how much overlap there is in the space of trajectories. The more overlap, the more likely it is to work. So on to some experiments to maybe make this more concrete. Here is a pushing task in which the goal is to push the cylinder onto anywhere on the red line. So that's task 1. Now task 2 is the same thing, but a different red line. Now if we want to do the composed, then the goal is to get to just the intersection, which is just the red in the corner. Now the key thing to note is that this last task right here, nothing new was trained. This was just by taking the Q functions from task 1 and from task 2. Oh, there we go.
So it's 0 shots. You do not retrain.
Correct. Yeah, no retraining. So yeah, no more data was gathered, and no more, even given the fixed data, we didn't have to retrain anything.
Reward? What is reward? Reward is at that point, or you combine, you add them together?
So you don't actually have to care. You don't actually have to care about the reward of the, like what is the reward of this combined task? I mean, you don't care about the rewards at this point. You're just combining the Q functions. Yeah. So they also show this on an actual real robot. So here's a stacking policy. So its goal is to stack the yellow block in its hand onto the red block, which is successful. And there's also an avoidance policy. Its goal is just to avoid where the green blocks are. Now, if you, this example is just kind of showing that if you just try to do the stacking policy where you don't take into account the green, like it's going to mess up. If you try to just do the avoidance policy, like congratulations, you avoid the green, but you're not actually accomplishing the joint task of also stacking the block. And now, if you do the proposed compositionality method by combining the two key functions, it can both avoid and stack the block. So this is, I guess, the real-world example of the 2D pushing that we just saw. OK, any questions on this before we get to the last topic? OK, last topic. So we're flexibility, and we're doing model-based. So this is some recent work that I did with some collaborators. Yeah, so let's jump in. It's going to be similar to kind of what we saw before. I guess my research, I have one kind of theme that I like to do, which is kind of models. So let's consider the standard reinforcement learning pipeline. We have our robot. It's gathering data. Then someone needs to label the reward function on this data. So for example, I'll sit there and say when a collision happened, when it didn't. And using this labeled data, we can then train a policy to maximize the sum of rewards. We use this policy to gather more data, and that's our reinforcement learning loop. And then at test time, we can actually just run this policy, and hopefully it'll work, and we can call it a day. But now let's say I want to accomplish a bunch of different tasks. Then you have to run this again and again and again for each different task. So I'd say that the standard reinforcement learning approach can be fairly data inefficient because you can't reuse data from any task. Basically, a lot of the methods are on policy. Even methods that are off policy, supposedly, like DQN, in practice, they tend to not be as soon as you go to neural networks. Another downside is you need some expert in the loop. So one thing I think in this class we've kind of assumed a lot of the time is that we know the reward. But when you get to the real world, it's actually fairly hard to know it. Oftentimes you have to sit there and hard code it, or you need to instrument the environment so that you know, here's my robot arm, here's the block, this is when I successfully put it on. So this is actually extremely non-trivial. And the last, which is kind of the main point of, at least of this section, is the inflexibility. Normally you train your policy and then it just does one task. You know, I train my collision avoidance policy, it only does that. And this is bad since we want to be able to do multiple things at test time. Next slide, cool. So kind of, I'll now give an overview of our approach for addressing this flexibility aspect. Well, all three, but mostly the flexibility. So first, we're going to have our robot gathering data according to any control policy. So we had the car, it was driving around on 5th floor of Corey, if that looks familiar to you, and put into just one big data buffer. Then we as a human, we sat down and we decided, okay, what event queues, what things are going to be relevant for the robot? So by event queues, it might be, oh, did a collision occur? What's my heading? Like, where am I looking? Is there a door that I can see? Are there pedestrians? Things like that. I'll call those event queues. And what we do is we train a model to actually detect each of these event queues. And now instead of us going through the data set, the detector goes through the data set and does all the labeling. Now using this, we can train our CAPS model, which I haven't talked about, but it'll be very similar to what I showed before. And then at test time, what we do is we specify the reward function in terms of these event queues. So it's not normally during reinforcement learning, you define the reward during training. And then you run and you do that. Now it's just at test time. So you get a lot more flexibility. You gather data once, you train once, and then you can do a bunch of different things. So kind of the pros of this approach are it's data efficient because you can use data from any policy. It's a detector in the loop, not a human, so this is much cheaper. For example, one of the detectors I trained took 200. I had to label 200 images, but the whole data set had 150,000. So at least for me, that was an advantage.
So what do you change in the testing time? What do you change?
At test time, which is the flexibility aspect, you change the reward function. So you can, to make this even more concrete, think of homework 4, you trained your model, your dynamics model, and then at test time, you can define the reward function that you want it to do. So if I know the dynamics of the half cheetah, then at test time I can say run forward, run backwards, and you can use the same model.
So it's model-based?
Yes, so this is model-based in that. Yeah, I'll get into it a bit more, but this is model-based in that sense.
Then you run MPC?
Yes.
Then you change the reward, you change the policy? Okay.
Correct, correct. So that's kind of why I like models. So that's my bias in all of this. So now to get into just the quick details, there's 3 phases to CAPS: detect, predict, and control. So detect, I basically already explained it, but you take event queues in some small data set to train your detector. Some of these are very simple. So collision and heading, you can directly get these from the sensors. Our robot has these sensors on board. Now, one that's more complicated is door. If I want my robot to maybe do package delivery and drop things off of doors, it needs to know where they are and what they look like. So to do this, we just trained a segmentation model, again, on like 200 images. And from this, we could then extract the reward from the segmentation model. So what it was actually predicting was the fraction of door that it could see, so like 0.32. Now next, our predictive model. This should look very, very similar to before. Just instead of predicting just collision, it's predicting all the event queues. So it predicts collision, predicts heading, and also predicts, like, is there a door for all time steps into the future. And again, we're not predicting future states. That would be standard model based. We're not doing that because we don't care about future images. We only care about these event queues. This is actually the neural network model, not just a bunch of clouds. It's not too important, but I guess I'll briefly touch on it. So we pass in the past 4 states. This is what you guys did in homework 3 for Q-learning. Pass through a few convolution layers. We then concatenate the vector part of the states. So these are things like how fast am I going? Just anything that's not an image. Pass these through some more layers, and then we have this recurrent neural network here, that's an LSTM, that processes each action sequentially for some fixed horizon. For example, we did about 12 to 16 steps into the future. And then from the hidden state of here, we output each prediction for each of the event queues separately. So this might be for collision, this will be for heading, this will be for door. So they share a bunch of the weights, just not the very end ones. Okay, and now finally for the control phase, what you'll do is you define what reward you want in terms of the event queues, and then you optimize for a sequence of actions to actually achieve this reward function by doing MPC and doing some optimization method. For example, you could do what you did in homework 4 with the random shooting method. You could do cross-entropy method, which was the bonus in homework 4, any of these methods. How much do these optimization methods matter depends on how far you're actually optimizing into the future and how big your action space is. Our action space was small because it was just steering angles, and we were only optimizing 16 steps, so it wasn't too bad. But I'd say one of the main bottlenecks for model-based approaches is this planning part. So I think that's definitely an active area of research. Okay. Let's see, I'll briefly go through. So we had some experiments. This was, again, Carla, like you saw, I think, from the conditional imitation one. But we didn't have any expert. So we just let the robot, I think it was running Q-learning for collision avoidance. That's how we gathered data. And then using this, we labeled the following event queues: collision, speed, heading, and where's the lane, because we want our robot, our car to actually drive in the right lane, not just anywhere. And to showcase an example of flexibility, we had one model, and we said to both models, drive at 7 meters per second, avoid collisions, and drive either in both, like either lane, like it doesn't matter, or just drive in the right. And as you can see, just by changing with the single model, but just changing the reward function, we can actually get qualitatively different behavior. And this is kind of the whole motivation about flexibility that we wanted. For the sake of time, I'm going to skip a bunch of the other ones. They're kind of just showing the same thing, just also in the real world, and just jump straight to the flexibility takeaways. So I'd say the first is that we have goals as the engineers that we want our robot to accomplish. So actually carefully thinking about how we should integrate goals into our policies is important. It's not just another observation that you just put in. There is something fundamentally different between goals and observations. Model-free methods, I think, require extra care to know how to reuse them and combine them. It's not just out of the box combine them. While model-based methods are more flexible by construction, that's kind of the main advantage that model-based people tend to push. But with model-based, you have to do planning, the horizon is finite, and there's a bunch of other challenges you have to accomplish. So with regards to flexibility, you kind of have this trade-off between them. Okay, so I think we're out of time, maybe 2 minutes. Any closing questions or anything anyone wants to bring up? Okay, cool, thanks, and finish homework 5.